2 grounds on an electrical panel serve important purposes beyond just being backup protection. Firstly, redundancy is crucial. If one ground connection fails due to damage or corrosion, the presence of a second ground ensures that the electrical system remains grounded and protected from electrical hazards. Secondly, a low impedance path is vital. 2 ground paths provide backup to each other, significantly reducing the impedance of the grounding system. This ensures a low resistance connection between the electrical system and the earth, which is crucial for effective fault current dissipation. Thirdly, isolation of neutral current is necessary. The neutral conductor in an electrical system typically carries return current. By providing a separate grounding path for the neutral conductor, known as the equipment ground, it helps prevent neutral currents from flowing back into the grounding system, which can cause electrical noise and interfere with sensitive equipment. Fourthly, surge protection benefits from a second ground. When connected to a surge protection device, the second ground can provide an additional pathway for transient voltage surges to travel, thereby diverting them from flowing through the electrical system and protecting sensitive equipment. Fifthly, safety for maintenance is improved. Having 2 ground connections ensures that there is always a grounding path available during maintenance or repairs. This helps protect electricians and other personnel from electrical shocks. When running grounds for a 100 amps panel upgrade, using number 4 copper for both the neutral and equipment grounding conductors is generally appropriate. The National Electrical Code, or NEC, provides specific guidelines for grounding conductor sizing based on the size of the service entrance conductors or the rating of the overcurrent protection device. The NEC Table 250.122 typically dictates the minimum size of equipment grounding conductors based on the rating of the overcurrent device protecting the circuit. For a 100 amps overcurrent device, number 8 copper might be sufficient, but using number 4 copper provides a larger safety margin and lower impedance path. The grounding electrode conductor, which connects the grounding electrode to the panel's grounding bus, must also be properly sized. NEC Table 250.66 is used to determine the size of the grounding electrode conductor based on the size of the service entrance conductors. Since this is a 100 amps service, a smaller grounding electrode conductor might be permissible, but using number 4 copper ensures compliance and provides additional safety. The NEC also addresses the installation of grounding conductors. Grounding conductors must be securely fastened and protected from physical damage. When running grounding conductors on the outside of the house, they must be installed in a manner that prevents corrosion and physical damage. This may involve using conduit or other protective measures. The grounding electrode system must comply with NEC requirements. This typically involves connecting to a ground rod, metal water pipe, or other approved grounding electrode. The grounding electrode must be properly installed and maintained to ensure effective grounding. All connections must be made using approved connectors and methods. The grounding system must be tested to verify its effectiveness. This can be done using a ground resistance tester to measure the impedance of the grounding system. A low impedance path is essential for effective fault current dissipation. The equipment grounding conductor provides a path for fault current to return to the source. This allows the overcurrent device, such as a circuit breaker or fuse, to trip and to energize the circuit in the event of a fault. The equipment grounding conductor must be properly sized and installed to ensure that it can safely carry the fault current. Bonding refers to the connection of metallic parts to create an electrically conductive path. Bonding is essential for preventing voltage differences between metallic parts, which can create a shock hazard. The NEC requires that all metallic parts that are likely to become energized be bonded together. This includes metal water pipes, gas pipes, and metal building components. Ground fault circuit interrupters, or GFCIs, are devices that detect ground faults and interrupt the circuit. GFCIs are required in certain locations such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electric shock. GFCIs provide an additional layer of protection against electric shock. Surge protection devices, or SPDs, protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, utility switching, or other events. SPD divert the surge current to ground, protecting sensitive equipment from damage. SPD are recommended for all electrical panels, especially those that serve sensitive electronic equipment. Regular inspections of the electrical system are essential for identifying and correcting potential problems. Inspections should be performed by a qualified electrician. During an inspection, the electrician will check the grounding system wiring and other components of the electrical system. The electrician will also test the operation of GFCIs and SPD. Any problems identified during the inspection should be corrected promptly. Regular maintenance of the electrical system is also important. This includes cleaning electrical panels, tightening connections, and replacing worn or damaged components. Maintenance should be performed by a qualified electrician. Proper grounding is essential for electrical safety. A properly grounded electrical system protects people from electric shock and prevents damage to equipment. It is important to understand the principles of grounding and to ensure that the electrical system is properly grounded. The NEC provides comprehensive requirements for grounding electrical systems. It is important to consult with a qualified electrician to ensure that the electrical system complies with all applicable codes and standards. The number 4 copper conductors are appropriate for the grounding electrode conductor and the equipment grounding conductor. These conductors should be run on the outside of the house, ensuring they are adequately protected from physical damage and corrosion. It is also crucial to consult with a qualified electrician for proper installation and compliance with all applicable electrical codes and safety standards. An electrician will ensure proper connections, protection from damage, and adherence to local regulations. The purpose of having 2 grounds on an electrical panel extends beyond mere redundancy. It enhances safety and reliability by ensuring a low impedance path for fault currents, isolating neutral currents, providing surge protection, and ensuring safety during maintenance. When upgrading electrical panels, particularly in residential settings, several key considerations must be addressed to ensure safety and compliance with electrical codes. Firstly, the proper sizing of conductors is paramount. The ampacity of the conductors must be adequate to handle the anticipated load. This involves calculating the total load based on the appliances, lighting, and other electrical devices that will be connected to the panel. The National Electrical Code, or NEC, provides guidelines for determining the appropriate conductor size based on the load and other factors such as ambient temperature and the type of insulation. Secondly, the overcurrent protection devices, such as circuit breakers or fuses, must be properly sized to protect the conductors. These devices are designed to trip or blow when the current exceeds the rated ampacity of the conductors, preventing overheating and potential fire hazards. The NEC specifies the maximum allowable overcurrent protection for different conductor sizes. Thirdly, the grounding system is a critical component of the electrical panel. It provides a low impedance path for fault currents to return to the source, allowing the overcurrent protection devices to trip and to energize the circuit in the event of a ground fault. The grounding system consists of the grounding electrode conductor, the equipment grounding conductor, and the grounding electrodes. The grounding electrode conductor connects the neutral busbar in the panel to the grounding electrodes, which are typically ground rods or metal water pipes buried in the earth. The equipment grounding conductor connects the metallic enclosures of electrical equipment to the grounding busbar, providing a path for fault currents to return to the source. Fourthly, bonding is the process of connecting all metallic parts of the electrical system together to create an electrically conductive path. This includes metal conduits, metal enclosures, and metal water pipes. Bonding helps to prevent voltage differences between these metallic parts, which can create a shock hazard. Fifthly, ground fault circuit interrupters, or GFCIs, are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electric shock. GFCIs are designed to detect ground faults and interrupt the circuit within milliseconds, preventing serious injury or death. Sixthly, surge protection devices, or SPDs, are recommended to protect sensitive electronic equipment from voltage surges caused by lightning strikes, utility switching, or other events. SPD divert the surge current to ground, protecting the equipment from damage. Seventhly, proper labeling of circuits is essential for safety and convenience. Each circuit breaker or fuse should be clearly labeled to indicate the appliances, lighting, or other electrical devices that it controls. This makes it easier to identify and de-energize circuits for maintenance or repairs. Eighthly, regular inspections and maintenance are crucial for ensuring the continued safety and reliability of the electrical panel. A qualified electrician should inspect the panel periodically to check for loose connections, corroded components, and other potential problems. Maintenance tasks may include tightening connections, cleaning the panel, and replacing worn or damaged parts. Ninthly, compliance with local electrical codes is mandatory. Electrical codes vary from one jurisdiction to another, so it is important to be familiar with the codes in the area where the panel is being installed. A qualified electrician can ensure that the installation complies with all applicable codes. Tenthly, when upgrading an electrical panel, it is important to consider the future needs of the household. If there are plans to add new appliances, lighting, or other electrical devices in the future, it may be wise to install a larger panel with more circuit breakers or fuses to accommodate the increased load. The neutral conductor carries the unbalanced current from the load back to the source. In a properly wired circuit, the neutral conductor should not carry any current under normal conditions. However, in reality, there is always some imbalance in the load, which causes a small amount of current to flow through the neutral conductor. The grounding conductor, on the other hand, is intended to carry fault current back to the source in the event of a ground fault. A ground fault occurs when a live wire comes into contact with a grounded metal part, such as the metal enclosure of an appliance. The grounding conductor provides a low impedance path for the fault current to flow back to the source, allowing the overcurrent protection device to trip and de-energize the circuit. The grounding conductor is typically connected to the metal enclosure of the appliance and to the grounding busbar in the electrical panel. The grounding busbar is then connected to the grounding electrode, which is typically a ground rod or metal water pipe buried in the earth. The purpose of the grounding electrode is to provide a connection to the earth, which helps to dissipate fault current and reduce the risk of electric shock. The grounding electrode should be located as close as possible to the electrical panel and should be driven into the earth to a depth of at least 8 feet. The grounding electrode conductor, which connects the grounding busbar to the grounding electrode, should be sized according to the NEC. The size of the grounding electrode conductor depends on the size of the service entrance conductors. The equipment grounding conductor, which connects the metal enclosure of the appliance to the grounding busbar, should also be sized according to the NEC. The size of the equipment grounding conductor depends on the size of the circuit conductors. The grounding conductor should be installed in the same raceway or cable as the circuit conductors. This helps to minimize the impedance of the grounding path and ensure that the fault current flows quickly back to the source. The grounding conductor should be connected to the metal enclosure of the appliance using a grounding screw or other approved connector. The grounding conductor should be securely fastened to the grounding busbar in the electrical panel. The grounding system should be inspected periodically to ensure that it is in good condition and that all connections are tight. A qualified electrician should perform the inspection. Any problems with the grounding system should be corrected immediately. The electrical panel should be located in a dry, well-ventilated area. The electrical panel should be accessible for maintenance and repairs. The electrical panel should be protected from physical damage. The electrical panel should be properly labeled to indicate the circuits that it controls. The electrical panel should be kept clean and free of debris. The electrical panel should be inspected periodically by a qualified electrician. Any problems with the electrical panel should be corrected immediately. The electrical system is a complex and potentially dangerous system. It is important to understand the principles of electrical safety and to take precautions to protect yourself from electric shock. If you are not comfortable working with electricity, you should hire a qualified electrician to perform any electrical work. Remember to always turn off the power before working on any electrical circuit. Use insulated tools when working with electricity. Wear safety glasses to protect your eyes. Avoid working in wet or damp conditions. If you are not sure how to do something, ask a qualified electrician for help. Electricity can be dangerous, but if you take the proper precautions, you can work safely with electricity.